Picture a single afternoon, 66 million years ago. The sky over what is now the Gulf of Mexico is calm, blue, utterly unremarkable, until it isn't. A streak of light brighter than the sun itself tears across the atmosphere, and in less time than it takes to read this sentence, a chunk of rock, roughly the size of a small city, detonates into the crust, with a release of energy that no human instrument built since has ever come close to measuring directly. Continents shudder. Forests ignite from the radiant heat alone, hundreds of miles from the point of impact. Within hours, 3/4 of everything alive on Earth is on a countdown to extinction. That single afternoon is, strangely, one of the best places to start a story about how Earth became the world we live on, because it teaches us the one rule that governs everything that follows. This planet has never once been finished. It has been demolished and rebuilt, over and over, across 4.6 billion years, and here is the detail almost nobody sits with. It is only now, this very moment, standing at the rough halfway point between its birth and the day its own sun finally swells and ends the experiment entirely. Everything you're about to hear is chapter 1 of a 2-chapter book, and we don't yet know how the second chapter ends. To understand how a lump of falling rock could nearly erase all life in an afternoon, we have to rewind, past the dinosaurs, past the first forests, past the first heartbeat of any kind, all the way to a time when Earth wasn't a noun yet, just a promise suspended in a cloud of debris. Before there was a planet, there was only leftover material, the scattered ash of stars that had already lived and died, drifting as a slow, cold disk of gas and grit around a newborn sun. Gravity, working without hurry, began nudging specks of dust into contact with one another. Static charge and weak molecular forces did the rest at first, clumping grains into pebbles, pebbles into boulders, boulders into bodies large enough to have their own gravity and start attracting more material on their own. This is how every rocky world in our solar system was built, essentially by accident, through billions of tiny collisions compounding into bigger ones. Earth, when it finally accumulated enough mass to deserve the name, was nothing you'd recognize. Picture not a globe of rock, but a globe of liquid. Its entire outer layer, a restless, glowing skin, unable to decide whether it was solid or fluid, kept in that state by the sheer number of impacts still raining down on it and by radioactive elements decaying deep in its core, releasing heat with nowhere to escape. There was no coastline, no bedrock, no single square meter anywhere on the surface that could hold your weight. And then, before this half-formed world had any real chance to settle, something roughly the mass of Mars crossed its path. Scientists have given that wandering body a name: Theia. Though nobody knows exactly what it looked like before the moment of impact, because that moment is the only reason we know it existed at all. It didn't strike Earth head-on. It came in low and glancing, like a car sideswiping another rather than meeting it bumper to bumper. Even so, the collision was violent enough to blast a colossal volume of vaporized rock and molten material into space around the wounded planet. That debris didn't simply drift away. Within what may have been mere centuries, startlingly fast, on a planetary scale. It began collapsing under its own gravity into a single new body, orbiting close enough to Earth that it would have filled a huge arc of the sky, dragging tides not of water but of molten stone across the surface below. We call that body the Moon today, and it's easy to think of it as a passive decoration in our night sky. It isn't. That single collision tipped Earth's axis into the tilt that gives us seasons, accelerated its spin into a day only a few hours long, and, most importantly, installed a gravitational anchor that has kept our planet from tumbling chaotically on its axis ever since. Some planetary scientists suspect that without a moon of comparable size, a planet's tilt can wander unpredictably over millions of years, swinging climates from pole-melting heat to bottomless cold with no rhythm at all. In other words, the same impact violent enough to nearly break Earth apart may be the very thing that made it stable enough, later, to host anything alive. For a long stretch afterward, Earth remained something closer to a toxic furnace than a home. Its sky a dim, sulfurous haze rather than blue, its ground still too hot in places to solidify completely. But the inner solar system in that era was a chaotic shooting range, still thick with wandering rubble left over from planetary construction, and Earth spent an extended period absorbing hit after hit in what geologists now label the late heavy bombardment. Here's the twist. Many of those impactors weren't dry rock. They were icy bodies, comets, and water-rich asteroids, carrying frozen water and simple carbon molecules that had been locked away since before the planets existed. Every strike vaporized a little more of that ice into the atmosphere. Every bit of vapor eventually cooled and fell as rain, over what may have amounted to millennia of near-continuous downpour onto a crust still radiating heat. Water pooled into every low place the crust offered, and Earth's first oceans took shape. Not through some gentle process, but as the leftover residue of the very bombardment that once threatened to keep it lifeless forever. The oceans that resulted were, for a very long time, completely empty, vast, dark, and sterile. The most consequential event in the story of this planet did not happen anywhere near sunlight. It happened at the seafloor, in cracks where mineral-saturated, superheated water pushed up from below. Hydrothermal vents, chemically rich environments that needed no daylight at all to function. Down there, heat, dissolved iron, sulfur compounds, and simple carbon chains collided endlessly, in combinations too numerous to count, for millions upon millions of years. Somewhere in that ceaseless chemical churn, certain molecular chains stumbled onto a property no rock had ever possessed: the ability to make copies of themselves. These were the distant, unglamorous ancestors of RNA and DNA. Nothing about this required intention or design. Only enough time and enough chances for a workable combination to eventually appear. And once it did, self-replication essentially guaranteed its own spread. The first true cells followed. Microscopic, entirely invisible without modern lenses, and utterly indifferent to the very gas most complex life now depends on. To these early organisms, oxygen wasn't a resource. It was a corrosive threat capable of shredding their delicate internal chemistry. Then, a lineage of microbes discovered how to use sunlight directly, splitting water molecules to build sugar and, in the process, exhaling oxygen as pure waste. At first, the ocean simply swallowed it. Dissolved iron in seawater soaked up the new gas and rusted outright, staining shallow seas a deep red and laying down the vast striped iron deposits still mined today. But iron is not an infinite sponge. Once it was saturated, oxygen had nowhere left to go but up, into the atmosphere itself. An event so significant it's now called the Great Oxidation. For the organisms that had never evolved any defense against this newly abundant, reactive gas, it amounted to a mass extinction in its own right. For everything that came after, oxygen-breathing life included, it was the opening of a door that had never existed before. Earth's history doesn't drift gently between states. It swings, hard, from one extreme to its opposite. Following that oxygen-rich, relatively temperate era, a sharp collapse in atmospheric carbon dioxide, worsened by shifting continents, disrupting ocean currents, sent the planet into a runaway cooling spiral. Ice spread from both poles until it may have reached the equator itself. For stretches lasting millions of years, Earth may have resembled a colorless, silent sphere adrift in space, its oceans sealed beneath ice conceivably a kilometer thick. Photosynthetic life, only just beginning to flourish, was squeezed into whatever thin slivers of liquid water remained. Pockets near volcanic vents, or areas kept open by geothermal heat leaking up from below. What finally broke that deep freeze wasn't anything arriving from outside. It was the planet's own interior, still churning beneath the ice the entire time, pushing volcanic carbon dioxide up through cracks in the frozen shell for millions of years without pause. Ice reflects sunlight so efficiently that this greenhouse buildup had almost nothing to counteract for a long stretch. But eventually the balance tipped, and the thaw arrived all at once, geologically speaking. Kilometers of ice cracked and dissolved in what amounted to a blink of planetary time, releasing an enormous surge of ground-up minerals and nutrients into the newly liquid oceans. It was, in effect, an ecosystem starved for ages, suddenly handed an unlimited supply of everything it needed. That nutrient surge set the stage for the Cambrian explosion. And explosion is not an exaggeration. In a window that may have lasted only 20 to 25 million years, astonishingly short by evolutionary standards, the oceans went from a world of simple, mostly soft-bodied organisms to a churning ecosystem of complex animals equipped with structures that had never existed before. Eyes capable of detecting shape and motion, hardened shells and exoskeletons, jointed limbs, and predators purpose-built to chase down prey. This sudden arms race reshaped nearly every basic animal body plan still in use today. The ocean stopped being a quiet chemical solution and became, in a geological instant, a competitive, crowded, and often violent arena. Arguably, the moment Earth transformed from a planet that merely hosted life into one that was unmistakably, vibrantly alive. For roughly 3 billion years, everything alive had stayed confined to water. That changed a little over 400 million years ago, when simple plants, partnered with fungi that helped them extract nutrients from bare rock, began colonizing land that had never supported anything living before. Small invertebrates followed, and within a few tens of millions of years, the continents transformed into humid, sprawling forests of towering ferns and primitive conifers. Vegetation that pumped enormous volumes of oxygen into the air and, over time, compressed into the coal seams still burned for fuel today. A green, oxygen-rich world with abundant food was, in evolutionary terms, an open invitation to scale up. For more than 150 million years afterward, a length of time roughly 75 times longer than the entire history of our own species, dinosaurs dominated nearly every ecological niche available, from massive, long-necked herbivores rivaling ships in length to agile, armored predators, while their flying relatives, the pterosaurs, ruled the skies above them. Which returns us to where this story began. That single, sky-splitting afternoon when it all ended in fire and darkness, sunlight blotted out for months by pulverized rock and soot, food chains collapsing from the ground up, and roughly 3/4 of every species alive erased in what amounts to a geological instant. Every mass extinction in Earth's history has followed the same quiet, almost ironic pattern. Whatever manages to survive, however humble, inherits the world left behind. This time, it was small, nocturnal, warm-blooded mammals, many no larger than a modern shrew, that had spent the entire age of dinosaurs living in the margins, hiding in burrows, active mostly after dark to avoid larger predators. With the giants gone and ecological niches suddenly, catastrophically empty, evolution turned its full attention toward them. Across the tens of millions of years that followed, mammals diversified explosively, some growing to enormous size to fill the vacancies left behind, others adapting to air, ocean, or treetop life. Among the tree-dwelling branches, a lineage of primates emerged, favoring grasping hands, forward-facing eyes for judging distance, and steadily expanding brains. Then, in what amounts to the final few seconds on Earth's full 24-hour clock, a new kind of primate stood upright on the grasslands of Africa, freeing its hands entirely and carrying a brain built not just for survival, but for something new, sustained curiosity about its own existence. Everything that followed happened at a speed utterly unlike anything before it. In roughly the last 200,000 years, a sliver too thin to register as more than a rounding error against Earth's total age, this single species stopped merely adapting to its surroundings the way every organism before it had done, and instead began actively rewriting them. Fire was tamed. Language let knowledge outlive any individual mind. Farming, cities, written record, and eventually science followed each other in rapid succession, compressing what once took millions of years of evolutionary trial and error into mere centuries of deliberate invention. Humans spread into essentially every environment the planet offers. Polar ice, equatorial desert, the deepest ocean trenches. But that reach came bundled with a cost no previous species had ever imposed at this scale. Measurable climate shifts within a matter of decades, extinction rates rivaling the worst die-offs in the deep past, this time driven not by asteroids or frozen oceans, but by the accumulated activity of one species treating an entire planet as raw material. Which brings us back, one final time, to that afternoon over the Gulf of Mexico, and to the strange comfort in realizing it was only ever one entry in a much longer ledger of near endings this planet has survived. Earth's sun still has roughly 5 billion years of stable fuel left before it swells outward and finally brings this solar system's current arrangement to a close. That means the entire sweep of what you've just heard, the molten birth, the moon-forming collision, the frozen and then flooded world, the sudden riot of complex life, the reign and fall of giants, and the improbable rise of a species now capable of reshaping its own planet, makes up only the first half of the story. Nobody has written the second half yet. It could become an age in which humanity finally learns to act as a caretaker rather than a consumer of its only home, perhaps even the launching point for life to spread beyond it entirely. Or it could simply become one more chapter in a very long history of resets. A history that has never once waited around for any species, however clever, that failed to adapt quickly enough. For the first time in 4.6 billion years, though, the pen isn't being held by an asteroid, an ice age, or a shift in the atmosphere. It's being held by something that can actually stop, mid-sentence, and think about what it wants to write next.